Our next speaker is Sophie Blow from the University of Edinburgh. We're going to talk about combinatorial construct. Oh, sorry, is that right one? Combinatorial. Oh, I've got. Have I got the right?
It's a bit of a mouthful. Yeah, no, it is a
I'm just
combinatorial.
looking at it. It looks it's a different title now. So it's combinatorial construction of moduli space of flow lines in discrete Morse theory,
Yeah, it
or
is.
more briefly. Yeah. Over to
Yeah,
you, Sophie.
thank you. So today I'm going to be talking about flow lines in discrete Morse theory. So what's Morse theory, I hear you cry? It's basically analyzing the topology on a manifold by looking at the differentiable functions on it. And I wanted to take this into a discrete setting by, instead of looking at manifolds, looking at simplicial complexes, and instead of looking at differentiable functions, looking at discrete Morse functions. And my project over the summer was basically making an algorithm to pair up different flow lines and ultimately, in a way that you will see throughout this talk, prove that the square of the differential is 0, which is not a new result, believe it or not. But this was a new proof, which was very cool for a summer project for me. But yeah, without further ado, the original proof method that I kind of followed alongside, this was a smooth version that I found a discrete version of, but it expresses the differential, where this is the notation for the differential of a critical point x with respect to a critical point y as the number of flow lines modulo 2 between x and y. We only count modulo 2, so if there is an even number of these, then we're done, it's 0, we're happy. So as you might expect, the square of this differential is still looking at critical x and z, but passing through some critical y. And we call that a broken trajectory. You can kind of imagine breaking it into two paths. So what we want to do is show that the broken trajectories correspond to boundaries of the space of flow lines. And a particularly handy fact that we can use to do this is that the manifold that we get is compact. Using this compactness, we see that the number of boundaries of this space is even. This is just a fact that I'm telling you, and you can believe it, or you can go and find out why it's true. It's always even, and we get this evenness, which gives 0. We're all happy. The square of the differential is 0 in the smooth case. But I wanted to make it a little more combinatorial. So let's translate it. So as I said, instead of manifolds, we're looking at simplicial complexes. And you might not know what simplicial complex is. So to understand it, I'm going to talk about what a simplex is. So a 0 simplex is a point, a 1 simplex is an edge, a 2 simplex is a triangle, and a 3 simplex is a tetrahedron. Basically, an n simplex is an nth dimensional tetrahedron. And I would draw the 4th one if I could, but I don't have enough dimensions at hand. But basically, a simplicial complex is a gluing of simplices together. So say a triangle gluing together with an edge and then a vertex over here. It doesn't necessarily have to be connected. But this is a simplicial complex. But a discrete Morse function is how we're endowing our function on this discrete version of a manifold. So how do we make a function on a simplicial complex? Well, what we do is we take each individual simplex and endow it with a value. And that's what we do. So this is the slightly mucky looking definition of a discrete Morse function. Basically what it's saying is that in general, higher dimensional simplices have higher Morse value, except at one you can have one exception per simplex. For example, this 8 here, this 8 here is an edge, and this 11 is a vertex. Vertices are lower dimensional than edges, so we expect them to have lower Morse value than 8. But this is an exception, which we are allowed one exception per simplex. So I call this a Morse arrow. And we can have Morse arrows between simplices and their boundaries. It's kind of hard to see where the boundaries of each simplex is. Is 8 a boundary of 14? 14 is a face, and 8 is an edge. So yes, but 11 is not a boundary of 14 because you have to go down 2 dimensions to get there. It's kind of hard to see it like that though. So what we do is translate it into a Hasse diagram, which displays it very nicely in 2 simplices up here, 1 simplices in here, and then 0 simplices at the bottom. And in general, we're allowed to go down in dimension via gravity. We just slide down with the Morse function, but the Morse arrows give us permission to jump up dimension. And something worth noting is that 5 over here is kind of highlighted. He's on his own, he doesn't have any Morse arrows, and I like to say that he sees his brother jumping up dimension, very disapproving of them jumping about, and that's why I like to say he's a critical simplex. He's critical of the other simplices. That's how I like to remember. But so we're looking at these critical simplices in a Hasse diagram. And a particular Hasse diagram, to give you an idea of flow lines through a simplicial complex, is the tetrahedron. So if we take the tetrahedron given by A, B, C, D as the vertices, and then say that this is a critical face and this is a critical vertex, then we can imagine that this is kind of a representation of a sphere, because the face is kind of like a maximum and the vertex is kind of like a minimum, and we're traveling down through the simplicial complex to this minimum, like we flow down the sides of a sphere. And this is the Hasse diagram of this tetrahedron, and a flow line through the tetrahedron is a directed path in the Hasse diagram. So for instance, we go from ABC to AB to A to AD to D. This is what this path on the right is doing. So when we have a flow line, we want to seek out more flow lines because we're very greedy like that. So there are various things we can do. If AB we refer to as our intermediate simplex, which is where the magic happens, it's where you drop down twice in dimension. There are various things we can do at the intermediate simplex. The first thing we can do is we can insert a Morse arrow. So say say we have this flow line like so. We want to insert the Morse arrow belonging to AB. The only Morse arrow that belongs to AB is the one going up to ABD, which is this face here, if you can see that. So we go up to ABD, but then we want to resume the same path that we were on earlier. So we do this kind of unintuitive back arrow just to resume it. We will resolve it later. I know it's kind of annoying at the moment, but we have now a path through the simplicial complex that goes a slightly different way. Another thing we can do is we can flop this flow line. And flop is kind of a silly name for it. But basically, if I have this intermediate simplex here, and I still want to get from ABD to A, but I want to find the unique alternative way of getting down from ABD to A. I don't want to go down via this path. I want to go down via the other path. The only other path is this one here, via AD. So let's follow that path. That's a down arrow here. And the only arrow between AD and A is the up arrow. So we now have a new path. The final thing we can do is we can cancel. So if we have this path here, then instead of doing all this shenanigans, going down to A, going back up to AD, we can just cut all that out and just go straight down to D. So this is basically a crash course in the three operations that we can apply to a flow line. And in particular, notice that if the intermediate simplex here is critical, then it won't have any Morse arrows attached to it. So we can't insert and we can't cancel. This means that the only thing we can do when we get to a critical flow line with a critical intermediate simplex, all we can do is flop, which I relate to. But so we will use this information for the next slide. The algorithm that I ended up with, I first of all took a flow line, flopped it. If I had this redundancy of going up and down in this kind of way that I was talking about, then I'd cancel, then I'd flop. If there wasn't any redundancy, then I'd insert the Morse arrow, then flop. And since we're starting with flop and ending with flop, there always has to be an odd number of actions if we consider cancel, flop, and insert to be the active actions. There are always an odd number of actions between the start and the end of the algorithm. And that's going to be important for reasons that we might see later. So if we terminate at boundary flow lines, as I was saying before, all we can do when we get to a critical flow line is flop. This kind of restriction makes us think maybe it terminates exactly at critical flow lines. And to give us an idea of why that might happen, let's look at the moduli space of flow lines. So if we have a flow line F and we apply, say, flop to that flow line, and then say it's got a redundancy, so we cancel out that redundancy and get to another one, and we flop again and say our algorithm terminates there, and we call this flow line F prime. Then say that we, for the hell of it, want to apply the algorithm again to this new flow line we've got F prime. First we apply flop, and then we keep going an odd number of times, because the algorithm always has an odd number of operations in the algorithm to get to some F prime prime. But we can see that if we apply the algorithm again, we get back to F prime. In particular, if we apply the algorithm twice to a boundary flow line, we'll get back that boundary flow line. That's called involutivity. So the algorithm is involutive. And this is basically a connected component of the moduli space of flow lines, where each vertex of the moduli space is a flow line, and each edge in the moduli space is an action between two flow lines, which is kind of meta because we're talking about flow lines over simplicial complexes, which also talk about vertices, but kind of just zoom out and imagine you're talking about further away. The vertices are now the flow lines. So something else that we can do to get closer to our goal of proving that the differential squared is 0 is defining a sign on a flow line. In particular, if the sign of f is +1, then I can give this a little plus. Furthermore, every operation in the algorithm negates the sign of the flow line. So flop will make this negative, and cancel will make it positive and negative, so that the sign of f prime is -1. And then going back the other way, this will be negative, this will be positive, so the sign of f prime prime will be +1. And because there's always an odd number of actions between f prime and f prime prime, they will always have opposite signs. Another thing that's worth noticing is that this algorithm doesn't necessarily seek out all flow lines in this moduli space. So say we've got another flow line G. Again, we can seek out some G prime, and then seek out, maybe it's a bit further away, some G prime prime. This will be another connected component of the moduli space. So every instance of flow lines will be surrounded by two boundary flow lines. And in particular, these boundary flow lines are indeed critical flow lines. They have to be flow lines where you're double dropping at a critical simplex. So let's try putting all of this together. So if the square of the differential is the sum over all critical beta, the sum of all critical gamma, taking the signed count of flow lines from alpha to beta multiplied by the signed count of flow lines beta to gamma. Basically, what that's saying is take all the positive ones, subtract all the negative ones, and that's your number of flow lines. But there's kind of something we don't need to do there. We could just say, take all the critical flow lines through beta and sum up all of their signs. That will give us exactly the same thing. But there's another redundancy in there. We don't really need to specify beta. We can say, take all the critical flow lines from alpha to gamma. That will cover all of the critical flow lines through beta for all beta exactly once. So these are equal. But we also know that every critical flow line is a boundary of one of the equivalence classes of the moduli space. So let's take, for each connected component of the moduli space, let's just take a random flow line in there, apply the algorithm once, get to f prime, apply the algorithm twice, get f prime prime. Since each critical flow line occurs in one of these equivalence classes, these will be all of the critical flow lines we need. It will count all of them. And then using the fact that the sign of this is minus the sign of this, which we found earlier, we can substitute that in there. But then we're just subtracting, the same thing from itself. So we're taking the sum of 0 each time, which gives us that the differential squared is 0, very satisfyingly. And that concludes my proof. And these are my references, and I hope you liked my talk. Thank you very much.
Okay, well, thank you very much, Sophie. That was an excellent talk. Is there any questions from the audience at all? Okay, we've got a comment from Eleanor saying, "Great talk. Thank you very much." So one sort of quick question from me then is, this is your original proof here that you've created yourself. So have you actually published this proof? I didn't see it on the reference list there. So
Well, I didn't think to put it on the list. It's on archive.
oh right,
I've
okay.
submitted it. I've submitted it to be published, and it's going through the things.
It's going for review, is it? Okay.
Well, they've said that they're happy to take it. They need a few more things. So.
Okay, yeah. Okay, excellent. Yeah, I was just wondering. So I didn't. Yeah, I was. It seemed like a great piece of work. You hadn't published it from what I can tell from that list, but you told me you have now. So well done.
Oh, thank you.
Yeah. Just as a more general question, a lovely presentation. I liked how you used your annotation throughout. What tool are you using to do this?
So this is Notability on my iPad. I wrote it up in LaTeX using Beamer,
Mhm.
but I wasn't able to find a way of actually doing that on my iPad. And I did want to like draw simplices and do all of these things. So I decided to use both LaTeX and Notability to portray everything.
Okay. So I think we've come to the end of the session now. So I'll thank both the speakers for their talks.